Hello everyone, I am Toshiki Saito and thank you for giving this opportunity. As Houdini is my favorite CG tool, so I am glad to speaking here today. I'm engineer at Japan Medical Company and commissioned researcher at Tokai University School of Medicine and also freelance animation artist. And I use Houdini in all positions. At Japan Medical Company, I design a medical device and optimize the product manufacturing workflow. Japan Medical Company manufactures the clinical remolding helmets for infants. This blue helmet is our new product. I'll talk about this helmet later. At Tokai University, I participate in the medical research project. In this project, I am studying about treatment for heart arrhythmia. I analyze medical image of arrhythmia patients using Houdini. I also talk about this project later too. As an animation artist, I create watercolor-like animation using Houdini and After Effects. Two movies at left are current work. Upper left one was used as an opening movie as a designer event. Lower left one is created for the music video. And the center one is and the right one are private work. Today, I'd like to talk about my uses of Houdini in medical research and product design. So let me begin with product design using Houdini. All products in this section are patented. First, I'd like to explain Japan Medical Company. Japan Medical Company is a manufacturer of cranial remolding helmets for infants. The cranial remolding helmets is helmets to reform infants' asymmetrical head shapes. Infants' head symmetry are also called flat head syndrome. According to the UK National Health Service, there are two main types of flat head syndrome. One is called brachycephaly. The back of the head becomes flattened, causing the head to widen, and occasionally the forehead bulges out, and the other is called brachycephaly. The head flattened on one side, causing it look asymmetrical. The ears may misalign, and the head looks like a parallelogram when seen from above. And sometimes the forehead and face may bulge a little on the flat side. These problems are quite common, affecting around 1 every 5 babies at some point. Young baby's skull is still relatively soft and can change shape if there is constant pressure on a particular part of their head. So, for example, head asymmetry is caused by sleeping regularly in one position. To treat this head asymmetry, the helmet mold prominent side of the head and allow room for flattened region to grow. So the helmets have different shapes for each patient. So we are making custom-made helmets. To manufacture custom-made helmet, we use this workflow. At first, we get baby's head shape using 3D scanner, and the scanner exports STL file. Next, we create ideal symmetry head shape from the STL file. Then other shape data is imported to Houdini. Houdini processes the STL file and generates the helmet data. On this step, we set some parameters adaptively for each babies. And the final product is molded by 3D printer. This is our latest helmet. As it has many holes with a basket-like shape, the helmet is very breathable. And since it is separated into front and rear parts, it is very easy to wash. These features were well received by parents and medical staff. But because of this feature, the helmet has very complex shape. The helmet has very complex shapes compared with a conventional one. So to generate a complex model, the CAD tool we used before was not suitable because the CAD tool was inflexible to generate model which fits various shaped heads and unstable to generate basket-like complex shape and very slow to generate model. In our case, Houdini is very suitable. It is flexible, stable, and fast. To generate basket-like complex shape, we used UV mapping logic. UV wrapping and mapping logic. This logic was not implementable in the CAD tool. And to validate data, we take some measurements using VEX. For example, we measure the shell thickness, helmet weight, and distance between baby's head and shell. The point variable node and the measure node enable these measurements. Next, it is difficult for CAD to generate model with many holes, especially the Boolean process such as serial number engraving or hole punching were unstable. It often collapsed the model. To deal with the instability, we use VDB nodes. VDB nodes make the Boolean process very stable. With dozens of heads, our HIVE works without errors. And speed is the biggest advantage of Houdini. With CAD tool, it takes 15 minutes to generate the helmet model. By using Houdini, the processing time is reduced only 1 minute. VEX enables this speed because it supports much threading and parallel computation, which is difficult to use with CAD tool. To reduce processing time, we use the process monitoring. The process monitoring visualizes the heavy nodes. It helps us to optimize the node network. When constructed the network, the process took about 5 minutes. It was still fast enough, but it got even 5 times faster by the optimization. This speed helps us to increase productivity. Then let me show you. Okay, this is a HIVE file to generate the helmets. I'd like to talk about the structure of HIVE file. The main logic is in this subnetwork. And to generate the personalized helmet, we manipulate the parameters installed as the subnetwork. As this file is distributed to some staff, digital assets is too complicated for unfamiliar staff to control version. So I do not purposely turn this subnetwork into a digital assets. Though the HIVE file refers to some assets, I try to complete in one HIVE file. The inside of the networks looks like this. I can't show you for details, but I'll introduce only a part. The ideal head shape is loaded in this file node. And the helmet data is generated using parameters entered by the staff. Okay, let's get back to above. The nodes that require setting manually, such as draw the outline of the ears, is on the same level with the main subnetwork. First of all, I open the ideal head shape data. Okay, the ideal head shape is loaded. This is either symmetrical head shape data mentioned before slides. I use the sample data in this presentation. Show or hide can be switched using this checkbox. Next, let's display the reference lines and set of the eyebrows, neckline, and sidebars. As different lines move smoothly, it is easy to fine-tune. Okay, first set eyebrow height and let's set neckline height. Next, let's set the sidebars height. Okay, it seems good. Next, I'll set the line near ears. Check this box to display the ear outline. This network has the automatic ear controlling logic. So this outline is controlled automatically. But sometimes the logic doesn't work well because the meshes exported from the 3D scanner has variations in quality. So the meshes often has hole or fail to get ear shape or has no manifold geometry. If it doesn't work, we control the ear manually. Okay, let's click this button and activate the draw curve node. And control ear. Like this. The point generated by this draw curve node is visualized by this polywire node. The callback of this button is defined at this Python node. I automate as many operations as possible by using Python script. In case of the bottom, the Python script activated this draw curve node, and the template flag of the polywire node set to true. The draw curve is visualized by polywire node. Then I control the outline, and by clicking this return button, the selection is back to this main subnetwork node. Next, I'll set the opposite side ear outline. But at this time, the automatic controlling logic works well, so I'll go to the next step without manual setting. And this parameter controls distance between the helmet rim and the ears. If these parameters are set to 0, the helmet rim generated around the ear outline. And if they are set to 10, the helmet rim comes to 10 millimeters from the contour line. If you want to reduce the distance at top, you should decrease this top parameter like this. To save trouble, I reduce the parameter that I need to be set by brush up the logic. Then let's check the base shape, which is source of the final product. It looks nice. So let's go to the next step. Set the toggle named view mode to preview. Then Houdini generates the draft version of the helmet, which is generated without heavy processing. We can use the preview version to check for processing errors and or model collapsing. Then if it has no errors, we switch a toggle to product and generated the product data. During generate it, although the heavy calculation is performed, such as VDB creation or reducing polygon, still it takes only about 1 minute. Okay, let's generate the product model. Okay, the process is done. Then we need to validate the product data. We can visualize the measured values that needed to be checked by clicking this box. We can visualize the measured values that needed to be checked by clicking box. This visualizes the shell thickness by coloring. Okay, this visualizes the shell thickness by coloring. And this visualizes the distance from the baby's surface. And this is estimated weight, which cannot be shown due to corporate secret. This visual system makes the data check step in the manufacturing workflow faster and easier. If there is no problem in the validation, we save the helmet data by clicking this button. The callback of this button is also defined at this Python node. And the Python script saves the helmet STL data and the backup file which records parameters. In this way, we can generate the helmet data just by manipulating the parameters at this subnetwork. And it can be done without manipulating the logic in the subnetwork. Because of this system, even if you are not familiar with Houdini, you can generate helmet data easily, and it makes our workflow smooth and smart. Okay, the live demo is done. Thank you. Moving on to the next part, I'd like to talk about medical image analysis with Houdini. As I mentioned before, I participated in the medical research project at Tokai University. In this project, I analyze a medical image of heart arrhythmia patients. I'd like to introduce my uses of Houdini in this project. First, I'd like to explain arrhythmia. According to my clinic homepage, heart arrhythmia is an irregular heartbeat. Heart rhythm problems occur when the electrical signals that coordinate the heartbeat don't work properly. The faulty signaling causes the heart to beat too fast or too slow or too irregularly. Heart arrhythmia may feel like fluttering or racing heart and may be harmless. However, some heart arrhythmias may be life-threatening. Heart arrhythmia treatment may include medications, catheter procedures, implemented devices, or surgery to control or eliminate fast, slow, or irregular heartbeats. And radiation therapy is emerging as a complementary therapy when other treatment fails or is not feasible. And then we are starting radiation therapy for arrhythmia patient. These photos and figures show planning and treatment of radiation therapy. At treatment planning, the heart muscle region to be irradiated is determined through analysis of detailed electrocardiogram, and medical image such as computed tomography, nuclear medicine image. After treatment, the same examination is performed to verify the therapeutic effect and check for adverse event. So high accurate medical image analysis are important for appropriate treatment. Let me explain in detail of image analysis. We use a contrast-enhanced computed tomography and nuclear medicine imaging. Nuclear medicine imaging is a method of producing images by administering radioactive tracer. The tracer travels through the area being examined and gives off energy in the form of gamma rays, which are detected by a special camera and computer to create images the inside of your body. For example, in case of the positional emission tomography, LNF fluorodeuthyl glucose is administered. The fluorodeuthyl glucose behaves like glucose, in other words, sugar. It is taken up by glucose using cells such as cancer cells or inflamed cells. So, fluorodeuthyl glucose PET is used to find cancer or inflammatory diseases. As a tracer is also used in the nuclear medicine. For example, 99M technetium is used for evaluation of blood flow in the heart muscle. So, nuclear medicine image has lower resolution compared with computed tomography, but it can visualize how the tissue functions. On the other hand, computed tomography is also called CT. CT scan combines a series of X-ray images taken from different angles around your body and uses computer processing to create cross-sectional images of your body. And the contrast-enhanced CT is the CT scan using radio contrast agent. This is useful to highlight structures such as blood vessels or heart cavity that otherwise would be difficult to delineate from their surroundings. A CT image has high resolution, so it is good to get anatomical information such as tissue position or shape, but it could not visualize the tissue function. Then, to take advantage of both imaging modalities, the multi-modal image analysis using contrast-enhanced CT and nuclear medicine imaging is performed. In depth, to identify the outline of the heart, we use a contrast-enhanced CT image which has anatomical information. And to evaluate the heart muscle function, we use nuclear medicine image. The heart is oriented obliquely against the body, and different people have different heart shapes and orientations. We must align the heart orientation correctly. But in case of patient with heart problem, the heart muscle is often hard to see and the nuclear medicine image is blurred. So we use contrast-enhanced CT image to identify and align the heart position. And to perform precise analysis, we must exclude effect of the other than the heart muscle. Three-dimensional heart muscle mask is needed. But the nuclear medicine image is too hard to see to create the mask. So we also use contrast-enhanced CT image here as well. As described above, we align the heart or create the mask of heart muscle using the CT image. And we quantify the heart muscle function using nuclear medicine image. But these images are acquired by different scanners, so we need to align them precisely. The image analysis tool we use in the clinical environment is not suitable to do this, although it has the function to align multi-modal image. But in this case, there are too many image types to align in one tool because we use various kinds of the nuclear medicine imaging techniques such as MIBZ, technetium scintigraphy, and FDG PET. And in nuclear medicine, The quantitative analysis is important to evaluate the tissue function objectively. To quantify the tissue function, we calculate the amount of the tracer in the area being examined. The pixel value of the image is used in the calculation. And next, various analysis is performed. For example, in case of heart muscle, we divided the tissue into several areas and calculate the sum of the tracer amount for each area. As another example, we plot the temporal changes of the amount after the tracer administration. For research use, the image analysis tool we use in the clinical environment is not suitable. Certainly, the image analysis tool is useful for the widely used method, but the tool is hard to try the new quantify method. It can only be used for certain purposes. And as I mentioned before, it is inflexible to analyze by using multi-modal image. Even in this case, Houdini is suitable. With Houdini, various nodes enable rapid prototyping to try the new analyzing logic, and the result of the method is visualized easily with advantage as the CD tool. Like this, the heart muscle information is visualized in three-dimensional viewport. As I mentioned before, to analyze nuclear medicine image, we use the mask extracted from CT image. Unlike conventional tool we use in nuclear medicine, the Houdini is easy to manipulate in three-dimensional domain. So to summarize the points of my talk, I introduced our practical example of Houdini on medical image analysis and medical product design. At medical product design, the Houdini made our production workflow fast, stable, and flexible. And at medical image analysis, the Houdini enables flexible medical image analysis. That brings me to the end of my presentation. Thank you for listening.